tomorrow. And we'll cover basically the initial part of what we understand by crystal structure and reciprocal lattices, and herein what lies within. And mostly I've used the reference from Charles Kittle's, a very standard, well-known book. So if any of you, due to whatever reason, is not being able to follow what is being said, or there needs to be a better explanation, you can refer to that book. So it's by and large that Charles Kittle that I'm going to follow. Right. So condensed matter physics, or solid state as you may call it, is basically nothing but the study of crystals and the electrons in the crystals, right? And people were always amazed by the fact that what actually is the arrangement of the most indivisible particle in the system. So for a long time, people had the idea that there might be certain periodicities available, but it was not really sure that what kind of periodicity, what length scales are there, are different materials organized in different ways or not? If so, whether there is some kind of inherent symmetry that has a role to play, and things like that. So in this context, this all began with the discoveries of X-rays, actually. So after the discoveries of X-rays, it was convincingly and beyond doubt established that there actually crystals have a large periodicity which is available to them. And there were a series of publications that proved decisively about the crystal and its periodic array. So what do you understand by the periodic array of atoms? So ideally, it is an infinite repetition of identical structural units in space, and it can be described in terms of something that we known as a lattice. So lattice is nothing but a mathematical abstraction. So as we can see here, I have, if you can follow this, so we have drawn certain what we understand by a crystal. So lattice is nothing but a mathematical abstraction of where these periodicities are actually there. And not only because, and it is actually an imaginary thing, it doesn't really, so it's, you can imagine it's kind of a network or a net 2D analog over which you overlay. Imagine it is like a grid. On this grid, now typically you put atoms or group of atoms on each of these lattice points, right? This is what you call the typically known as the basis, right? And this basis put on a particular lattice in a particular arrangement, periodic. I'm showing in 2D, but it is actually truly acceptable in 3D as well, to get the final crystal. Now, the whole crystal structure is about trying to understand what is the arrangement that is actually inherently present in such kind of systems. And you will know already that, typically from our vector knowledge, that there is actually translational vectors which can carry you from one particular lattice point to any other particular lattice point in the crystal. And if you go from one lattice point to another lattice point, you basically don't see any difference, which means that if you are not aware of the operation of translation from one point to another, you would not realize that you have actually moved. However, when you are actually considering something like a basis, which means group of atoms, you have to also imagine that you locate the center of the lattice point which is at the, say here, at the center, and accordingly what is the position of the other atom or atoms with respect to the central atom. Okay, so this obviously will have again be defined by things which are by the axis of this particular crystal axis. However, their values x, y, and z will be much smaller than the unit of this axis here, right? So you can move from one particular lattice to another to a usual translation vector, and within the particular basis you can move by something which is a reasonable small number. These x, y, z are all fractional numbers because you are moving within that particular point. So this is what you understand in terms of the crystal structure, right? So it is lattice, we know, is now a regular periodic array. We have a 2D analogous, which is form of a net, and only it's a mathematical abstraction. So lattice plus basis gives you the crystal structure, right? So one thing which is important is that when you define something known as a primitive lattice, one says that actually there cannot be any volume which is less than the primitive unit cell. Okay, so minimum volume cell which extends to fill the all space, which means that if you look at this cartoon, this small section that I have actually shaded, and this is the one thing which will be propagated in 2-dimensional in this case, or 3-dimensional in case of 3D, and it can fill the complete volume. This is the typical definition of a primitive lattice. You will see that the contribution of per primitive lattice is also a shared contribution of the adjoining lattice points, and each of them contribute equally to form one lattice cell, one atom contribution per lattice cell, right? So we know about now the lattice translation operator, and we have now heard how we can go from one point to another. So finally, for the description of the crystal structure, what we do in X-ray diffraction, there are two or three important points which we need to know. First is, what is the lattice, right? Whether it is kind of a square or oblique or some kind of a different geometrical shape, right? What is the choice of ABC? In a second, I will show you what I mean by ABC. So you can just see that, when you have a lattice, you can define them as several A's, A1, A2, to define the boundaries of the primitive lattice. There can be numerous of them. So what is the right actually choice of A1, A2, A3? Because there will be more than one choices of the set of axes. And finally, what is the basis? So basis, which constitutes a group of atoms. And this can only be identified once the lattice and the axis have been carefully chosen, right? So from primitive lattice, now the question is that if I give you the problem, so here let us look at kind of an oblique kind of a lattice, which is the most generic form. And you will see that there are several cells, one, two, this is say the three, and this is four, and so on. All of them shaded differently in color. You will see that I can choose cell 1, but somebody else can also choose cell 3. So what is basically the unique choice? Because finally, when you are discovering the crystal structure, you want to say what is the lattice, what is the associated symmetry, and stuff like that. So the thing is that as far as the primitive lattice is concerned, there is really no limitations for that. Okay, you see, if I take A1, A2, this is one, this is the primitive cell, and this also satisfies the condition that it has the minimum area in this case, which can be used in space along X and Y direction to fulfill the entire space. But it is also true for two. So for instance, look at A1 and A2. Because look, when we look at the area of a parallelogram, what does it say? It is basically height times the base. Now, since the base is fixed, both this parallelogram and this parallelogram have same area. So 1 is also acceptable, 2 is also acceptable, the green shaded one, 3 is also acceptable, it is the green shaded one. However, if you look at this number 4, where A1 and A2 have actually much bigger area, because this cannot be taken as a primitive lattice cell, because you see that in this whole area there is actually a small section of the area which is already the smallest area that is available. When I say area, it is unit area. You can call it in terms of lengths or volumes or whatever you like, but this is already the minimum. Hence, this cannot be considered as a primitive cell. So these are the certain conditions, and based on these conditions, we have sometimes different classifications. So what do you mean typically when you talk about the area? You talk about this base into height, but when you talk about the volume, you basically you look about the parallelepiped associated with that. So volume is basically nothing but the A1 dot A2 cross A3, A1, A2, A3 being the three axes. And when it comes to sharing about atom per unit cell, how does this work? So you look here, I have considered in this case, so this is say 1, and there is 2, 3, 4. These are the adjoining lattices. So when you look at this green atom, it is shared by these 3, 2, 1, and 4, each contributing 1/4. So from each corner, you get 1/4 contribution. Similarly, for the red one, the contribution will be 1, 2, 3, 4 in this condition. For here, it will be from these adjoining and so on. So you will see that for this unit cell 1, there is 1/4 contribution from each edge point here for the atom. So total, there are 4 corners, each contributing 1/4, which gives you 1 atomic contribution per unit cell. If you look at for the volume, it is something very similar. For say a simple cubic arrangement, you see where you have defined A1, A2, and A3 as the 3 axes, and you will see that each of this corner is shared by 8 adjoining such cubes, or in this case parallelepipeds, and you will see that your contribution is coming from these 8 corners, which are contributing 1/8. Hence the total contribution per lattice cell is also 1. So this is the primary condition that you have to put when you're talking about a unit cell, which is a primitive unit cell. Okay. There is another way to create this primitive cell. I mean, if you're not really sure and you don't know which one to do, there is something which is known as the Wigner-Seitz way. So what do? In first step, you connect the nearest neighbor. So for instance, you are looking at this central atom. So you connect the nearest neighbor on the top, bottom, left, and right. Now you bisect this perpendicular line. So this line, there is a perpendicular bisector. this line there is a perpendicular bisector, similarly here and here. And now you find that the area enclosed by these perpendicular bisectors of the connecting nearest neighbors is actually going to give you the Wigner side cells, and in essence that is exactly what is your primitive cells as well, right? So this is a very, nice way to realize if you are not really sure what is the primitive cell associated with a particular group of lattices given here. So you can try, for instance, as take-home exercise, the Wigner site cells for rectangular, hexagonal, oblique, and centered rectangular lattice. We'll talk about the classifications here, but you see that it is not only here for a square. It is rather easy to understand how it is, but for a hexagonal or other oblique lattice which is not uniform, it might not be so easy to understand how it is done. All cases, you join the nearest neighbors and you take the perpendicular bisector and you find the area which is trapped between these perpendicular bisectors, and that essentially gives you your Wigner side cell or the primitive cells, right? And Wigner side cells also has a lot of implications when we talk about reciprocal spaces. I'm going to take this up again, but this is exactly how you create the Wigner side cells. Okay. So when we talk about lattices, there has to be a classification, isn't it? So you talk about the fundamental types of lattices. What exactly do you understand by these fundamental types of lattices? So what it turns out that it all has to be typically, based on the differences in symmetry. How, I'll tell you. Now, when you talk about, the symmetry is a larger, in the larger context, is a more, I would say, fundamental thing. But imagine that there is a particular lattice across which you are doing symmetry operation. Symmetry operation means either you are rotating it with respect to certain angle, or you are doing some kind of a mirror reflection, or you are doing a translation. So there can be different kinds of symmetry operations. Either they can be about a point, or about a translational operation, or a combination of both. However, just look here that if I keep on rotating my unit cell, say by 2 pi, which I'll call one fold, or 2 pi by 2, or 2 pi by 3, and you will see successively it gives you very well defined structures, right? So you will see that the lattice cells or lattices will have certain inherent type of symmetries based on their main, what is the way in which they have been defined. For instance, this lattice here is only one fold symmetry. However, if it is a rectangular one, it will be two-fold. If it is a triangular one, there is threefold. If it is a square, it will be fourfold. If it is hexagonal, and so on. So there are many, many different ways in which the fundamental types of lattices can be classified. What doesn't work is, for instance, say five-fold symmetry, which means twice pi by 5, or seven-fold symmetry. So although pentagons and heptagons are like regular geometrical shapes, you see that if you try to connect different pentagons together, you will always be left out with certain space that you cannot fill, right? So in the context in which we are trying to define our fundamental types of lattices, five-fold symmetry or seven-fold symmetry doesn't exist. Hence, they cannot be classified under the fundamental lattices. Now, based on this symmetry argument alone, and based on how you make, for instance, either the collection of symmetric operations about a point, which means rotation in most cases, or reflection or inversion, or space group, which means that you are actually making some translation, and sometimes even combination of translation as well as rotation or reflection and inversion. These are, however, a little bit more complicated things. But what I mean to say is that when a lattice is moved from its original position to another, and if it follows certain symmetry, then you can easily classify them in 2D and 3D, right? So you will see that it is known that there are about 32 point group symmetries. These are what is a set of the symmetric operations about a point that are allowed, and accordingly 230 space groups. And based on that, you will see that in the something that define as a Bravais lattice, okay, over these 32 point groups and 230 space group, there can only be in three dimensions the allowance of 14 types of lattices in three dimensions. Whatever is allowed in these symmetrical conditions, we call them the Bravais lattice. Okay, so I will just show by example for 2D first, and then we'll come to the 3D. So let us see for the 2D lattice how it goes. So oblique lattice is basically, it is the most universal type of lattice. Here there are no restrictions. Now, remarkably, you will see that the moment you start, so when you talk about a 2D net, what are the parameters that you should be aware? If you want to know about the lattice, you have to know about A1, you have to know about A2, and you have to know about the angle between these two, which is phi, the oblique one, isn't it? So what turns out is that whenever you put restrictive conditions, then the most generic lattice, which is the oblique lattice, will undergo different kinds of classifications. So the first lattice, the universal 2D lattice, is oblique lattice. However, the moment you make certain restrictions, for instance, if I make A1 equal to A2, in the first one, see, A1 was not equal to A2, and phi could have been anything between 0 and 180 degree. I had no restrictions. It is all falling under the oblique lattice category. However, the moment I put that A1 and A2 should be same and phi should be equal to 90, it turns out that we are immediately going from an oblique lattice to something which is known as a square lattice. Now, obviously, there is an advantage over this, because while in the oblique lattice, our number of unknowns were three, A1, A2, and phi. In our square lattice, there is only one unknown. Phi is 90 degrees, already well known. A1 equal to A2 equal to A. So you go from a situation where the three unknowns were defining a particular situation to one unknown, which is much more easier for you to solve, right? It's just a matter of an equation, how many parameters you have to find from there, and it is much more easier if the situation is more symmetric, right? So okay, from square, it might not be always that restrictive. I can say still fix phi to be 90. However, A1 might not be equal to A2. In that case, you see the lattice looks like a rectangular lattice, right? So each and every restriction, either big or small in terms of the lattice axis parameters or the angles enclosing them, gives you well defined ways. Similarly, look at the hexagonal lattice. Here, A1 equal to A2 and phi equal to 120 degree. So this is the fourth type of 2D lattice that comes into play. Apart from that, so these four, by the way, are all primitive lattices, because it kind of fulfills all our criteria of having the smallest volume or area, and total contribution to the lattice is one atom. So they are oblique, square, rectangular, hexagonal, are all primitive by definition. However, there is another lattice in 2D, this also known as the Bravais lattice, which is not a primitive cell. This is something we call the centered rectangular. So if you look at this lattice, there is basically the rectangular lattice is there, and then there is one atom sitting at the center. This unit cell will have two lattices per unit cell. Okay, and this by definition is now no longer a primitive cell. If you want to make a primitive cell, it will be looking like something like this, what I have actually drawn here, right? A1 is not equal to A2, hence you cannot define this as a hexagonal lattice anyway. But you will see that instead of having another oblique lattice, I am classifying this as another lattice which is not necessarily primitive in its definition, but I am still considering it as a lattice. Why? Now you understand, and I hope I've been able to convince you that in all of these situations, a symmetry of the lattice plays an important role. My overall goal is to estimate the lattice parameters, which means like your lattice constants A, B, C, alpha, beta, gamma, and stuff like that. And the more symmetric the crystal or more symmetric the lattice is associated with the crystal, it is much more easier. For instance, it's much easier to solve for a cubic lattice than it is to solve for a, say, trigonal lattice or rhombohedral lattice, because of the symmetry factor, because there are less number of parameters that you need to find out from your equations. So I am compromising on have this being a primitive lattice, because I know that rectangular lattice has more symmetry associated with it. I will exploit this symmetry in my calculations when I'm actually picking out the unit cell parameters and solving the crystal structure. And I will ignore that there is, although a primitive lattice always exists for such kind of lattices, but I still, it is a common knowledge that, for more symmetric kind of unit cells, you may as well use them, and hence this is the fifth lattice. And in 2D, thus you have five types of Bravais lattices. Okay, so centered rectangular, although not being a primitive cell, is still considered as the fifth Bravais lattice. The other fours by definitions are actually Bravais lattices. And now we can go to the 3D part, and we will see that how this restriction is actually classification is important. So as I told you that symmetry considerations tell us that in this 3D Bravais lattices, the point group necessitates 14 different lattice types, which means that in the whole world, whatever type of crystal systems you get, it will definitely fall under one of the 14 different lattice types. It cannot be anything else. I mean, it has not been found till date. People are doing diffraction for so many years, more than hundreds of years, but it is clear that they cannot get anything that is more than the 14 different type of lattices types, right? And let us again try to generalize this as we did for the 2D. You will see that the most generic lattice is triclinic, and the other 13 lattices are special triclinic lattices on which we impose certain kind of symmetry restrictions, right? And you will see that these 14 type of Bravais lattices can actually be for convenience clubbed into the 7 types of crystal structures. Okay, so for instance, look at this cubic lattice. In this cubic lattice, we know that everybody knows that there can be simple cubic, body centered, and face centered cubic. Now if you remember the definition that I introduced about the primitive cell, only the simple cubic is something which can have a primitive lattice. The others, where either there is a one sitting at the center for a body center, or for something which is sitting at the face for a face centered, this is not a primitive lattice by definition. But we still prefer to use body centered cubic BCC or face centered cubic FCC lattices, because as I explained earlier, they are more symmetrical. They are still cubic, right? So I don't mind taking care of this extra atomic contribution as long as I'm benefiting from the inherent symmetries of the cube, which is a big advantage for me, because I only need to know one parameter, which is A. I don't want to know A1, A2, phi, and stuff like that. One, A1, A2, A3, all are equal to A, and this is 90 degrees. So if I can handle this extra atom in my consideration, then I am happy to include or invoke a cubic lattice, even though it might not be typically a primitive lattice. Okay, and this is what, so this is this cubic lattice is that type of lattice which has now 3 types of lattices, and likewise you can define 7 types of cell in which these 14 Bravais lattices in 3D are distributed. Okay, so let us have a look at them. So triclinic, as I explained to you. So later on, I have a view graph, and I will show you exactly how it looks in 3D. It's actually difficult to draw a little bit. However, so in the triclinic, which is the most generic 3D lattice, you have one number of lattices. You have restrictions on angles. So A1 not equal to A2, not equal to A3, alpha not equal to beta, not equal to gamma. And this is the most generic type of lattice. And this is what a triclinic lattice typically looks like. See here. So there are point groups. So forget for the time being the Schwanflies notification and others. These are not important because we don't have the time and the bandwidth to go much deeper into this. But you will see that in the triclinic, there are the 14 Bravais lattices can be described in this 7 crystal systems or crystal family, like triclinic, monoclinic, orthorhombic, tetragonal, hexagonal. Well, you can call it rhombohedral or hexagonal, and cubic. And in each of these, in the cubic family, you have 3 Bravais lattices distributed. In most of them, there are 1 or 2, but in orthorhombic, there are actually 4 types of Bravais lattices. Whether it can be primitive, which means this is one unit, contribution is one atom. It could be body centered, it could be face centered, it could also be something which is known as the base centered. Okay, so typically, so this is what we will come to. However, let me try to finish this argument that we started here. Yeah. So triclinic, as you saw, is number 1 lattice, and nothing is equal. A1, A2, A3, all not equal. Alpha, beta, gamma, all not equal. Alpha is the angle between A1, A2, beta between A2, A3, and gamma between A1, A3. So this is the convention that we are typically going to follow in this case. Okay. Also for this monoclinic, you will see that here what I put the restrictions is that I still A1, A2, A3 are not equal to each other, but alpha and gamma, you impose the restriction of being 90 degree. Okay, and this is not equal to beta. So beta is free, but alpha and gamma are 90 degrees. So I have reduced the number of parameters associated with this crystal structure. And in the monoclinic system, two type of lattices can exist. One which is primitive, which is we have already by definition. The other is base centered. Now primitive by definition is going to have one atomic contribution per lattice side. Base centered will actually have two, because it is at the top base and at the bottom base. So there is basically contribution coming from the top and bottom, right? Similarly, from monoclinic, and we are going from the less symmetric to the more symmetric as we go progress further and further in our classification. So in this orthorhombic, you will see that actually four types of lattices present, right? Which is primitive, it can be body centered, as I explained for the cubic. It is similar for orthorhombic, something sitting at the center, at the body, along the diagonal, halfway through it. It can be sitting at the faces, which you call the face centered. It could also sitting at the bases, top and bottom bases. So the sharing is only between top and bottom. It is not across the other faces. Here you see still A1 and A2 and A3 are not equal to each other, but all the angles are otherwise equal to 90 degrees. So we keep on increasing our restrictions on the lattice parameters, as we call them, or the angles and axes as I've defined here, and we go from triclinic to monoclinic to orthorhombic, and then from there we go to something which is known as a tetragonal. Here all of this alpha beta gamma is 90, and two of these axes are actually equal to each other. A1 is equal to A2, the lattice parameter is equal, and only one lattice parameter is not equal to them. So it's tetragonal. So it's basically the difference from cubic is that only cubic A3 is also equal to A1, A2. Here A3 or the C axis is actually different than the A1, A2. In tetragonal also there exists two type of lattices, both primitive and body centered. It does not have base centered or face centered or otherwise. In the cubic, I already explained that there can be primitive, there can be body centered, and there can be face centered. And these are the restrictions that we have already discussed. And from cubic, we would go to trigonal or rhombohedral situation, where A1 equal to A2 equal to A3, alpha equal to beta equal to gamma is less than 120, but not equal to 90 degrees. Okay, so you see gradually that we have actually, and hexagonal is the most symmetric, where A1 equal to A2 not equal to A3, alpha beta equal to 90, and gamma equal to 120. So this is basically, remember the symmetry, what fold number of symmetries we're talking about. This is the most symmetric structure. So now you see that in the 7 crystal systems, the 14 Bravais lattice can be distributed, and these are all based on restrictions and the symmetry that they are showing with respect to their positions, right? So you can typically define any kind of characteristics of a lattice. Cubic is the easiest one, but through this you can do any, basically hexagonal, orthorhombic, whatever you want. And when you look at a particular lattice, what are the most important points that you should be trying to understand? These are, say, volume of this lattice, right? So what is the conventional lattice points per unit cell, volume of the primitive cell. All of these are important because they are to be supposed to be given during the crystallographic information, right? So you can easily see that for a simple cubic lattice, the volume is A times A times A is A cube, and this is the same for BCC and FCC. However, lattice points per unit cell, when it is 1 for the simple cubic, it is actually 2 for the body centered cubic, and actually 4 for the face centered cubic. So I will, whenever next time I show you the figure, I will tell you actually what are the contribution coming. So just you can say that there are 6 faces of a cube, and each one sitting at the face is giving you half a contribution. So you have 8 edges, which is giving you 1 contribution, and 6 faces, which is giving you half each, which means 3 contributions. So total contribution per unit cell is actually 4. Hence, when you consider the volume of the primitive cell, you have to subsequently divide it by 2 because of this 2 lattice points per unit cell, and 4 because of this 4 lattice points per unit cell. So this is, in essence, I have now included in my formalism a way in which I can handle the extra atom or atoms, however maintaining the symmetry of it being cube. As long as I know that my volume of primitive cell is now different, I can handle the fact that there are how many number of lattice points per unit cell, and then it doesn't really matter too much in terms of the other considerations. I will show you later that this BCC and FCC, which are innocuous looking cubic structures, have a rather difficult looking geometrical primitive lattices. And if you want to work with this primitive lattices, it has its advantages in some cases, but in most cases people prefer that you work with the BCC and FCC formalism because of the symmetric associations with that. Okay, so Many other things are important. For instance, the number of nearest neighbors, how many numbers nearest are there. So I just left it blank here, but you should be able to figure out that how many number of nearest neighbors are there for the BCC and an FCC, right? So I want that when you look at this lecture, you work it out and see nearest neighbor distance, number of nearest neighbors, second nearest neighbor, and stuff like that. Another important aspect is known as packing fraction. So packing fraction plays a role in how well a particular crystal is packaged. Okay, so how do you define it? You define that, see, a typical atom looks like a sphere, isn't it? Now this sphere, if I try to fit into this unit cell, which is in this case say a cube, what is the packing fraction? Packing fraction is the total volume of the sphere divided by the volume of the cube, and it can never be 1. Obviously it can always be less than 1, right? So the more the packing fraction, the more the better is the packing of the atoms within that unit cell and overall periodicity. And this has its manifestation in a lot of other properties, right? So some are more densely packed, some are less densely packed, and it has its consequence in other physical and chemical properties as well. So packing fraction also becomes important. We'll also discuss this in a little bit detail, particularly in the cubic case. Okay. So this I already explained to you. These are the typical three-dimensional manifestations of how they look like. So you see, this is the primitive for the orthorhombic. This is the body centered. This is face centered, and this is base centered. So there at the base, at the top and bottom, you have this extra atoms associated with that, right? And that also has to be taken into considerations. Now, the moment what I was saying. So, see, primitive lattice, well, now you have actually smartly circumvented the problem of not going into the botheration of a primitive lattice, right? But when you do any kind of diffraction or you do any kind of measurement, that doesn't know that you have actually cheated the system and that you have created a new body centered cubic system, right? Where you have included an extra atom because for your convenience of calculation. But the whenever you are doing diffraction, the diffraction will come, and often when you look into one unit cell to another, that transformation through reciprocal space happens using only the primitive lattices. So it is important to know what is the primitive lattice associated with the body centered cubic. Now look at this image. The one with the white border is actually a body centered cubic, right? At the center you are seeing this. However, if I have to calculate the primitive cell, then I have to exclude the one sitting in the center, right? So my unit cell will be such that there can only be one atom and their contribution can only come from the edges, essentially. So now this is typically the primitive cell, and this is nothing but a rhombohedron of edge root 3 a by 2 with an angle 109.28, something like that. Okay, and this definitely is, not so easy to work with. You are much better off if you have a cubic lattice. However, we should know what are the primitive lattice translation vectors of this BCC, because often you speak people saying that, what is a reciprocal of BCC, and you find it is an FCC, or what is a reciprocal of an FCC and you find a BCC. But in order to do this transformation, to prove it, or to go from one particular lattice to another, you have to invoke the primitive translation vectors associated with that. So I have shown with this figure, this is the central positions, and my lattice vectors or translation vectors for the primitive lattice will only be associated with the three body centered parts of three adjacent cells shown here. This is my x axis, this is my y axis, and this is my z axis. And the only way I can actually create a rhombohedron or a primitive lattice is if I connect these 3 points from one particular, say, so called center, which I am considering at this confluence point, and I go and I have to connect with the body center of either going towards the y direction, or going towards the x direction, or going towards the z direction. Now all I need to do is I have to find out what is this a1, a2, and a3 corresponding to a, which is already known. A is my distance between two atoms here, right? So you look at this a1. So where is this a1? So a1 is basically lying in your xy plane. So if you look at here, you will see that you have a x that is 1, y that is also 1, but z, which is in the negative direction. So a1 is nothing but half. Sorry, this is because it's a body diagonal, so it's at the center. So it should be x by 2, y by 2, and minus z by 2. And if you take this out, a by 2, your lattice translation vector a1 will look like x plus y minus z. So this is my primitive translation vector. That is important to remember. Similarly, if you look at a2 and a3 the way you have defined, in this case I have defined a2 here. So from here you have to go halfway along y, halfway along z, and halfway along the negative x, right? So a2 will look like a by 2 minus x, because see, this atom has actually gone in the negative x direction, right? It is towards the not going towards positive x but negative x. So you have a by 2 minus x plus y plus z, right? And similarly, A3, which is the third point here, is actually in halfway down along X, halfway along Z, and half of halfway negative Y. So it is A by 2 X minus Y plus Z. So this is my primitive translation vector. These are the vectors that I use when I will create a reciprocal lattice out of it. And only then you can prove that from how you can go from a BCC to an FCC or vice versa. But unless you do that, there is no way to prove it, because they are all cubes. How can you make a reciprocal lattice of one cube to another cube? So there is something inherently conceptually important and different here. And for that, the primitive lattice or the knowledge of it is rather important. Volume, of course, for all of them is similar, a1 dot a2 cross a3, right? This is the scalar product that you usually associate it with, right? Fine. So in the similar lines, what is the primitive cell of an FCC lattice? Again, we can actually formulate. So this is now, from when you look at the FCC, you have to look at all the face centers, top, bottom, left, right, left and right, and other sideways, right? So you will see that from this central point, if I define my lattices as a1, a2, and a3, you will see very easily that for me it is much more easier, because this is lying in the yz plane. So there is no x. So for this point there is no x, for this point there is no y, and for this point there is no z. So accordingly your a1 will be a by 2, of course, because it is sitting at the center point of the diagonal x plus y. A2 will be y plus z, and a3 will be z plus x. Now, it doesn't matter what direction you choose, A1, A2, A3, as long as you are consistently doing it. If for one you are choosing the XYZ in one direction, if for the other you are changing, then you are actually going to be facing difficulties proving it, right? But now these primitive lattice vectors, and this is the typical primitive unit cell of an FCC, which is also not a cube, right? It is also it's definitely a regular geometrical shape, but definitely not as symmetric as one associates with the cubes. Okay, so the primitive cells associated with FCC, BCC, and others should be known. For the simple cubic, of course, it itself is a primitive cell, so you don't need to know about it. And there is only one unit vector A which can define all the parameters, right? So this talks about the different kinds of crystal system lattices and Bravais lattices associated in 2D and 3D. And I hope I've been able to explain to you why there are 14 type of Bravais lattices, and why not all of them are primitive. And even if they are not primitive, what is the advantage of using non-primitive lattices? Because here we want to leverage the symmetry associated with the regularity or the ease of doing our operations, right? So it's much more easier to handle a cubic system, as you typically know. Okay, so another thing which is very important in the context of these crystal systems and lattices is the index system for crystal planes. So you can imagine that, more often than not, you will see that the orientation of plane is determined by 3 points in the plane, which are typically not collinear, isn't it? So if I have a particular axis a1, a2, a3, right, and I want to, and this is the plane that they are subtending, and I want to define how I identify this plane, right? Because remember, whenever you do X-ray diffraction and other things, you get different planes. You say 100, 121, and so on and so forth. So what exactly is that index system, and how you can actually calculate that, or how you can identify a particular plane in these situations for a crystal, right? So what is the typical process? So first, what you do, see, the moment you see from the defined origin, you see that what are the 3 points you have. The plane is intercepting A at 3a, so 1 2 3, this point here. It is intercepting a2 at 2a, so 1 2, and similarly a3 at 1 and 2. So you have plane intercepting at 3a1, 3a2, 2a2, and 2a3. Now what you do, the first step that you do is you take the reciprocal of these intercepts. So what is the reciprocal of the intercept? It is 1/3 here, 1/2 here, and 1/2 here. Now, as you have done in your schools, you look at the smallest three integers with the same ratio, and immediately you can realize that this is nothing but it is 2 3 3. These are the smallest three integers in the ratio, which tells me about the reciprocals of the intercepts. And this 233 is now something that I call my Miller indices, or indexation of a plane. Hence, the plane that I have shown here and which is highlighted with yellow is actually the 233 planes of this particular crystal system, right? And this is given by the Miller indices H, K, L. H associated with X, K with Y, and L with Z. Mostly people try to ascribe them in this order, but if you're changing it, you should be doing it consistently, right? So this is what is known as the Miller indices of this particular system. And sometimes what happens is the plane, just like your line, might not intercept positively, but it can also intercept in a negative, which means in the different direction. There can be planes who have negative intercepts. In that case, wherever you have, say, minus k or something, you put a bar on top of that. So if you look at a crystal plane system 1 1 bar 1, you know that it is H is 1, K is -1, and L equal to 1. So this is exactly the way in which this index system works, and this is defined by the Miller indices. Okay, and this is very important because it is actually conceptually important to understand that what are the planes, how do you define these planes. And if you are given some kind of a, say, blank crystal system, you should be able to identify that. It is very crucial to understand what are the planes that you are actually reflecting or diffracting when you are looking at diffraction patterns or other patterns, right? For instance, say 100, right? So 100 typically is this, this yellow shaded plane that I've in here. 100, it is intercepting at a1 at one point, and 00, which means that it has no intercept along a3 and a2, which means it is parallel to this a3 a2 plane, right? So this is basically the plane that is highlighted in yellow, is the 100. Similarly, you can have 010 and 110, which means the plane which is intercepting at around a2 or a3, and they are actually parallel to the other axis here. You can think about 110. Look at 110. So look at this kind of the violet shaded part, which means that the intercept in a1 is also around 1, at around a2 is also 1, but this is parallel to the a3 axis. So you have like 110, right? So similar context, you can have 101 if it is cutting along two different axes. There's something which is parallel to the a2 axis, or something which is parallel to the a1 axis. Another important thing to note here is that if you look at 200 plane, right, remember, we are always looking at the intercept, not at the actual. So 200 doesn't necessarily mean, as a lot of students sometimes suffer from this misconception, that it might be double. It is actually half, right? So if you define the 100 plane, which is here, if it is 200, which means it is intercepting the a1 axis at half the distance. So this yellow plane is actually midway between the origin and the 100 plane. Okay, it is definitely a higher order, but because we have defined our Miller indices by the intercepts, which is a reciprocal, it is 2. Similarly, 300, which means it has to be further down, which means 1/3. So if you have a higher index for H, which means that the planar is actually closer in terms of its distance to the origin. Okay, so this thing is very important to know. Typically, when you have 1 bar 00, which means that you have a1, a2, a3 axis, but instead of having 100, which is in this direction, you are having it in the opposite direction. As you can, this is probably not a great figure, but I hope you understand that A3 is intercepting at -1, and this plane is parallel to the A2 A3 axis. So this tells me it is like a 1 bar 0 0 kind of a plane. So these are very important and conceptually important. So you have to visualize and realize that what are those different planes. I mean, 100 and 110 or 111 are perhaps a little bit easier, but if you look at more complex planar structures like 1 2 3 bar or stuff like that, you can be able to actually understand that what are the planes associated with this crystal structure that is actually giving you a favorable diffraction. These are very important because, as in later classes we will see, that there are actually restrictions that come on the various diffraction properties associated with different crystals. For instance, there might be n number of such crystal planes, but not all of them will appear if you are doing some kind of a diffraction measurement, right? Now, what defines that? What are the mathematical conditions which tells me that, okay, for a BCC certain planes will be allowed, certain planes will not be allowed? For FCC certain planes will be allowed, certain planes will be not allowed. This all has to do with the definitions of the indexation or the HKL values here associated with that. We'll come to that later, but at that stage it is important to understand what are the different planes. Only if you understand what and where the planes are, you will be able to understand why and why not these appear in certain specific diffractions. Okay, another thing which is important is the crystal directions. It is not often taught to students, but you have to imagine that, particularly if you are doing analysis, you will see that directions and planes are completely different things, right? Because crystal direction is that line joining two points, beginning at one particular point and ending at another particular lattice side, right? So for instance, if your blue is at 0 0 0 here, and the orange point you define here. So orange point is what? 1 2 3 4 times along positive in a direction, 2 times along negative in a direction. So you have 4a minus 2a. And what do? You take this 2a common, so it is 2 minus 1, or it is 2a, 2 1 bar, because we don't say minus in directions or planes, we say bar. So basically the crystal direction along this line is actually 2 1 bar. Because it is 2D, that is why you have only 2. If it is 3D, you would have one more index to add to the third dimension, right? So this is the Miller indices for direction. Similarly, you can define for the red point here with respect to this arbitrary point 0. You can also do between two respective points. They need not be with always with respect to the center or the origin. They can be between -1 3 and 3 1. So you will have x2 minus x1 and y2 minus y1. So all you need to do is subtract -1 from 3 and subtract 3 from 1, which gives you something like 4 minus 2, or 2 common 2 minus 1, or 2 1 bar. So this direction is actually 2 1 bar for this direction. So these are some ways in which crystal directions and crystal planes are known to be defined in the literature, and it's actually a very good practice to have, right? So I'll just show you what the different crystal directions are. See, so this is a 0 0 1, this is the 1 1 1, this is 0 1 1, and so on and so forth, right? And look at, these are the different crystal planes. This is a 1 0 0, the plane which is shaded. This is 1 1 0, which is cutting A and B both at one, and this is 1 1 1. See, it is cutting of both A, B, and C, or A1, A2, A3 at these three values. So the plane which subtends these through points which are not collinear is actually the 1 1 1 plane, right? There are several equivalent planes, as I told you, in sometimes, and it is very important to understand that, if you have to identify these planes, often you probably also get problems in where you see that, okay, what is this plane? So you see 1 0 0 I have already shaded here, but if you were to look at 1 bar 0 0, you could go in the reverse direction, and this would be 1 bar 0 0. 0 1 0 plane, look, here it is, because it is cutting the A2 axis at 1, and it is parallel to the A1 A3 axis. Similarly, 1 bar 0 0. So with respect to that, it can be either above or below that particular plane where the intercepts are happening. Look at the 1 1 0. So you look at the intercepts here and here. So all the 1 1s are easy because the intercept of 1 is 1. But the moment you go to 2 or something else, then you have to be a little bit careful, because the intercept would actually mean half of what the value is already given, right? So if you are using somewhere these bars, say 1 bar 1 1 bar, and you have to shift the origin with respect to that, and then define those crystal planes. This is actually an important exercise to keep in mind and remember that what actually defines. So for instance, this 1 bar 1 1, this is actually this plane which is defining here, and it might not be very obvious, so it looks very easy when it is being shown. But I encourage you all to just draw this and try to, without any help, try to figure out what is the 1 bar 1 1 plane corresponding to, say, the easiest the crystal system of the cubic system. And you can now imagine that the more complex the crystal system gets, it is even more difficult to educate what particular crystal planes are associated with that. Okay, so another very important point about packing is the planar density. Just like I spoke about the packing fraction, I will speak about the planar density. How do you define a planar density? Planar density refers to the density of atomic packing in a particular plane. So now look at this yellow plane, and this is basically how many number of atoms is there on the plane divided by the area of a plane. So if you just look at this yellow plane, this is how it looks like. And imagine now this distance is actually root 2 times a, because it is a diagonal of this square here, isn't it? So if you look at this, you will see that there are actually how many atomic contributions happening? There is 1/4, 1/4, 4 from the four corners, you get 1/4. And from these two sitting in between, because of this face centered lattice, you will get half contribution from this atom, half contribution from this atom. So these two will give me total two atoms, one coming from the four corners and two coming from the side atoms. And so the number of atoms on this plane is 2 divided by the area of the plane. Area of the plane is root 2a times a, which is a root 2a is a square. So your planar density for the 110 particular plane is root 2 by a square. Okay, so this is how you calculate planar density. You can do it for 100, 111, any type of planes. You can draw first the plane, you see how many atoms it is actually cutting through, what is the contribution of this atom to that particular planar density, and finally you will be able to figure out, when you normalize that with respect to the area of the plane, that what is its planar density. Similar for linear density. Here it is rather easy to say, you look at number of atoms in the direction vector divided by the length of the direction vector. For instance, if you are still looking at the 110 direction, which is this one, you see the vector is cutting from 1, 2, 3. So there is contribution happening half into two corner atoms and one which is coming from the center atom. Remember, this is a line, so the other atoms don't really count. I am only counting through a particular line. So they are contributing half for these lines and one full. So you have two, and the distance is of course also root 2a, because it is the diagonal of a square, and hence your linear density of a 110 is also root 2 by a times, right? So then basically you can look at the different crystal directions, different planar lattices, and from there you can actually calculate that what is the most densely packed direction of the FCC lattice or a BCC lattice or some other lattices, right? So planar density, linear density, these are very important. And finally the volume density, or otherwise known as the atomic packing factor. So I will finish this and then we'll take a quick break before we resume for the next class. So here let us look at a BCC crystal, and I hope this 3D rendering gives you a much better picture of what it actually looks like. So this atom is actually touching all the edges here, right? So you will see that there are 4 and 4, 8 atoms at the corner which are contributing 1/8, and there is one big one sitting at the center here, right? So this total gives me the total effective number of atoms per unit cell is 2, and the relation between RNA is what? You are looking at the distance from here to here. So this is the atomic radius R, the atomic radius R plus R, 2R plus R. So there are actually 4R, and this is the body diagonal. What is the body diagonal of a cube? It is basically root 3 times A. So I have the relation root 3A equal to 4R. And now I define the atomic packing fraction as total number of atoms times the area of one atom divided by the volume, sorry, not area, sorry, volume of the cube. So you see this is 2 atoms times volume of each atom divided by the total area of the total volume of the unit cell. And this gives me something of a value which is 0.68. Okay, because I know that A and R are related. So this gives me a packing fraction which is obviously less than 1, but still a reasonably larger number, right? So packing fraction also tells me that in which kind of crystal configuration you can have maximum number of atoms that can be packed together. and that all of course has a lot of influence on its mechanical, electrical, and other properties also, right? Because you know that crystal structure is central to other physicochemical properties. So I think I'll stop for the time being. If there are any quick questions in the chat, I'm happy to take it.
Yes, Professor Banerjee, we can take a break of 5 minutes. Let us see if candidates have written anything in the chat window. Dipesh, can you please check whether anyone has written any question in the chat window? This is the same window. So it seems there is no question. Maybe we can take a break of 5 minutes and then we can again start the second lecture. Okay, okay. One question is there, Professor Banerjee.
Hmm.
Pooja Pal is the candidate and she is writing, sir, what is the spinal structure?
So, if you are listening, see, spinel structure is a special structure. I mean, we have not reached to that level where I can explain to it in the framework that we have done. But I will try to address this at the maybe end of this lecture, fourth lecture series. I will address this question. Right now, it is a little bit premature from my end to be able to explain it.
Okay, 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 yeah. And another question, another candidate, Lakshmi is writing, one is from K. Lakshmi Narasimha Rao is writing, what is that I should not from today's talk in connection with quantum technology? So she just want to know that whatever has been taught in this lecture, how we can connect it with the quantum technologies.
Well, I mean, I think this is the whole point, right? Isn't it, Professor Singhal? So,
Yes,
condensed
yes,
matter
yes.
is at the heart of anything. Quantum technology is just not a buzzword these days. It is based on very years of experiments done in condensed matter physics, right? And optics. And now they have come together at an instance. If you don't understand the typical way the periodicities, the crystals, where the electrons are with respect to these atoms and how they are arranged, you cannot even talk about the different quantum behavior that they might have, right? So crystal
Yes.
structure has a lot of role to play in any kind of physicochemical properties that one sees. And although we are trying to cover this is a very basic solid state, perhaps in modern quantum technology and cavities and all, we don't talk about it in that fashion, but it is very important and central to quantum technology, nanotechnology, and stuff like that.
Yes, yes, agree. If we do not know about the basics of solid state physics, we cannot understand the quantum mechanics or quantum physics. And if we do not know all these things, then we cannot even talk about the quantum technologies because any technology is based on some theory, some fundamental concepts. So first, in order to go up to the quantum technology, we should start from the basics of solid state physics, and that's same thing Professor Banerjee has taught in this lecture. So I can take few more question. One question is PPT PDF provided or not? Yes, we will be providing these lectures recording. These all the lectures which are being delivered by different speakers in this FDP. The recording would be available through Canva link on you. These all have been recorded, and we will be providing through Canva's link, and through that you can open the YouTube video. Canva is having some problem today. Some maintenance issue is there from the Canva administration side. I hope by today evening it will be resolved, and then you can again log in from the Canva where you can get the link to see all these recorded videos of the lectures. Okay, so
Excellent.
one more question. Yeah, Minakshi is writing, sir, I want to research in spintronics, how it is related to it. So candidates are writing whatever they have there in mind, and it seems
So
that candidates are very curious and
yeah, it's a good thing. See, I hope there has been enough interest which is sparked, and throughout this lecture series, I mean, I am just taking a few lectures on that.
uh-huh,
Gradually, when you understand the nuances of phonon,
uh-huh.
specific heat, Fermi level, and all this nicely curated, and it is this I am targeting to all audience. You will
Yes,
understand that this the concepts of magnetism, superconductivity, and topological insulators, quantum materials, spintronics, all of these are actually related. Okay, and these are just trying to brush up the basics. So there is no shortcut to be directly be able to do spintronics tomorrow. There is a process through which you have to learn this, understand how things are, go through this grind of it, and only then you will be able to focus on specific aspects of magnetism, superconductivity, or quantum technologies that are there here. Yes, so we cannot, given the context or the framework of this program, it is very difficult. Perhaps a one-on-one interaction can be more helpful, but given there are too many participants, I think we will try to stick to, if there is some question relevant to the lecture material, which I'm more than happy to explain.
Yes, yes, Professor Banerjee, I agree with you. So what we can do, we can take a quick break, and after that, Professor Banerjee will be delivering second lecture. And at the last of the second lecture, I will try to take all the relevant questions from the participants so that Professor Banerjee can respond them within the limit of this syllabi of this lecture.
Perfect, perfect. Okay, thank you.
Yeah.
So we meet in another 5 minutes.
Yes, yes. So
Okay.
we participants, we will take a break of 5 minutes, then we will be back. It's 4:40, then around 4:45 or 4:46, we would be coming back, and then we would start second lecture. At the last of
Yes.
the second lecture, I would try to take other questions also, as well as these previous questions also, which are relevant to these topics. Thank you.
Excellent. Very good. Very good. Okay. So I'm there. Just I'm muting it. Huh.
Okay, okay, sir.
Okay.
Okay.
Okay. Okay, welcome everybody. I hope I didn't drive everybody away. So the screen is still visible, I hope.
Yes, sir, it's visible.
Okay, excellent. So just going forward, I mean, typically, we now have spoken about the different kind of Bravais lattices in 3D and the different ways in which atoms are packed in linear direction or area or volume, right? And these packing fractions and all basically gives you a good idea about, for instance, when you compare cubic systems, like simple cubic or body centered or face centered, which among them has the most highest packing fraction, right? Which means that along what is that particular crystallographic orientation along which maximum number of atoms can be accommodated per unit cell, isn't it? So these are very important perspectives, but also important are typical some examples of this crystal structure, right? So for instance, sodium chloride, and this is where I'm trying to give you 3 or 4 case examples of these crystal structures because these are important, and they don't necessarily, although they can be classified in our classification of the crystal systems, what we it cannot be done is that it looks slightly different than what it actually is, right? So look at the sodium chloride structure here, and here chlorine is this green atom, sodium is this small atom here. Each sodium ion is surrounded by 6 nearest chlorine, and the same is with the chlorine. Okay, now if you look at this image directly, what is your first instance? What do you feel like is this typical crystal structure looks like? Now see, it is very difficult if you look at only one particular block, this which is shaded by red, and it is actually created by these different blocks here, different units. You will see that it is actually an FCC lattice where the sodium and chlorine are separated by half of the body diagonal. So essentially 0, 0, 0 and half, half, half. So there are 4 units of sodium chloride in each unit cube, which is at a position 0, 0, 0, correspondingly half, half, half. Then half, 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 correspondingly 0, 0, half. Half, 0, half, correspondingly 0, half, half. And 0, half, half, correspondingly half, 0, 0, 0. Now this is important to understand that these atoms, they are different now, they are two atoms. So this is not just iron or cobalt or something else which all atoms are same. And how have we defined more than one atoms? We already define them as particular bases, which means that the sodium and chlorine together form a basis ascribed to one lattice point, and the sodium chloride structure is then an FCC of this total particularly well defined sodium chloride structure. Okay, so sodium and chlorine you should not mix, you should always pair them up. For instance, in this case you have this 0, 0, 0 and half, half, half. So these two atoms here are actually part of one lattice site, right? And from here to here the distance is half, half, half. Remember I told you that within if you are finding something within the basis, all these numbers from here to here are fractional values, because if you go from 0, 0, 0 to 1, 1, 1, you reach somewhere else, you can reach somewhere outside. But because this is at somewhere in between, this is basically two atoms belonging to that particular basis, but only one lattice point is considered. So these are all pairs of these lattices that are there. And when you are looking at the scattering power of the sodium chloride, all of these 4 units of sodium chloride along with their positional coordinates have to be taken into account. Okay, fine. So maybe it's a little bit easier to explain with cesium chloride. So if you look at the structure, cesium chloride, you will see that this red one is chlorine, which is sitting at the center. Now at a first instant, what do you think this lattice should be? This lattice at the first instance looks like a body centered cubic, right? Because at everywhere there is atom sitting, and then at the center there is another atom. But no, this is not a body centered cubic, this is a simple cubic lattice. Why? Because this is a different atom. cesium and chlorine together, they are forming one kind of a basis. So now your atomic basis is something looking like a dumbbell, if you I can explain this. And this is the lattice point, right? So the lattice point is this. So lattice point, in each of these point there is a cesium associated, chlorine associated with the cesium halfway along the body diagonal. So these, they form a pair, cesium and chlorine, they form the basis, but the lattice point is only one point, as we have already defined. So this is nothing, it is not a body centered cubic, it is actually a simple cubic structure, right, with a coordination number which is now 8. So cesium, if you put cesium at 000, the chlorine will be respectively at half, half, half. This is just one structure which I showed for the cesium chloride. In sodium chloride, there are 4 such units that contribute to it, right? And many such examples like beryllium, cuprate, copper, zinc, ammonium chloride, and stuff like that, they crystallize into this kind of structure. So this is important to understand, that something that apparently looks like a BCC might not be a BCC. You have to identify the basis. And this is even more important. If there is one type of atom, yes, it is BCC. But if there are 2 types of atoms, you should be careful before you designate to the particular crystal system, right? The another thing which is very important and well known in this is particular the hexagonal close packing. Now, what is this hexagonal close packing? As you can see here, this is typically this hexagonal close packing. So there are like 1, 2, 3, 4, 5, 6, and one sitting at the center, right? So you will see this looks like a hexagon. Each point of it is like a triangle, right? Now this is happening at the base. In three dimensional, what happens is that you see that there are certain gaps between these 3 atoms. There is certain gaps. So what the next layer tries to sit on the gaps. These gaps are now these blue gaps. Look at these blue gaps. So I'll put my atoms on top of this gap. So on top of this A layer, I now have a B layer, which is trying to put this gap. Now, depending upon how I put my third layer, C layer, which is the blue atoms here, I can either have a hexagonal close packing, or I can have a face-centered cubic type of a structure. So the hexagonal close packing structure essentially is always A, which means after A layer there is B layer, and then again on top of it A layer is repeated. So A, B, as you can see here. A, B going. So this is a typical hexagonal close packing. If, however, after B there is some other arrangement, which is say C in this arrangement, then this is no longer, it is hexagonal, but it actually can be classified also as a face-centered thing. So this is important. The ABA hexagonal close pack structure where the layers are there. So C layer, or you see this is a C layer. If you put a C layer, then it is known as a ABC face-centered cubic. If it is ABA, it is a hexagonal close pack. If it is ABC, it is face-centered cubic. So just depending upon whether A type is repeated or the atoms go slightly somewhere else, which I'm showing with this blue atoms or blue lines here, these are actually C type. This is actually no longer a hexagonal close packing. So hexagonal close packing, this is the base, this is the A bottom, this is the A on top, and in between sits B. So the way it is coordinated, you will see that there is a basal hexagonal plane. On top of this, there is some C distance above. Somewhere in between here is basically another triangular plane, and on top of it, you have another A type plane. And now there is a 6-fold axis, which means that every pi by 6 rotation will actually go, 2 pi by 6 rotation is going to give you the same result in terms of symmetrical configuration. So this is important aspects to look at the hexagonal close packing. So how do you define those basis points here? See, now you look at a conventional unit cell. This is a conventional unit cell. What is this? This is an FCC, because there is an atom sitting at every face. 1, 2, 3, 4, 5, 6 of it. If I create a primitive unit cell, which I showed you a while ago, that how the primitive cell can be constructed. Look at this green structure here. It is a primitive cell. It is not a cube. So it has less symmetry, but it does not include extra atoms in between. So it's a primitive cell. Correct? Now, in this primitive cell, if you put an A, B, C type of structure in a hexagonal cell, in this conventional unit and primitive unit cell, if you put a hexagonal structure, look at this A. This is hexagonal, then is another basal plane, there is another basal plane here. So these are the 3 triangular type of lattice which are organized on top of each other, although it a little bit shifted with respect to each other. This gives you a hexagonal structure. So A structure. But if you look at from this direction, it can also be ABC structure. Got it? So there is a difference. ABA and ABA. So these are different planes altogether now. See, ABC. ABC is nothing but, I told you, FCC, or face-centered cubic. You will see that both the face-centered cubic and hexagonal close pack have a packing fraction of 74%. I encourage you really to work out using the formula that I've discussed, that just like I showed that for a BCC, your packing fraction is about 0.68 or 68%, you should try doing this for the FCC, right? It is very easy to do it. Only you have to remember how many extra number of atoms are there per unit cell, and how they are related with respect, the A is related with the radius of this atom, right? No structure, regular or otherwise, can have a denser packing, which means the densest packing possible is 74%. Nothing can be more than that. Okay, till date, no material is found, no crystal structure that has a packing fraction of 75%. 74% is the maximum that you can get, right? So you see, this is typical way in which the hexagonal. So how do you define these, the basis of two atoms, because you will need for your calculation, isn't it? So you look at this hexagonal pack, and now you just take out this section point here, right? Because you need two basis points. So when you take this section out, this is how this section looks like. This section has this basal plane A and B, and there is another atom which is sitting somewhere here. Now this atom sits at a position which is 2/3 of A, 1/3 of B, and half of C, right? So from with respect to this, it is 2/3 of A, 1/3 of B, and half of C, right? 2/3, 1/3, and half. So here you will see 2/3, 1/3, 1/2. These are the basis of the two atom. One is at 0, 0, 0. We always put one at 0, 0, 0 for our calculation ease. So one atom is here. The other point with respect to the hexagonal close packing is at 2/3, 1/3, and half. And another thing which is important is that you probably also know that A is equal to B, but the C by A ratio is actually given by root over 8 by 3. This is also actually a small interesting calculation. It's actually just geometry and mensuration. That's all you need. But you can just look at where this C, the atom of this position is, and you can easily figure out a relation between the C value, the C which is here, and A equal to B. So this C by A ratio is root 8 by 3. This is very well known for hexagonal close packing, and you can also actually calculate that using simple geometry, right? So hexagonal close packing and FCC are important crystal structure configuration, because there are no structures which can have a more dense packing. Another very important structure is that case of a diamond. Now this is a little bit of a different idea, right? Why? Because diamond is what? It is made up of carbon. However, the case of diamond, the crystal structure of diamond was not studied, because diamond is a very valuable. Of course, it is valuable, but that is not why its crystal structure becomes so important. It is so important, the crystal structure, because silicon at that point of time, which was the main ingredient for the semiconductor revolution and the silicon semiconductor age that we are now living in. Hopefully, next generation will be for quantum technologies or AI. But right now, our generation mostly is dominated by silicon electronics. Silicon is actually crystallizes in this diamond crystal structure form. That is why it becomes so important. But here you will see that instead of looking at it in a more complicated way, the case of diamond becomes much easier to visualize if you consider that there are actually two FCC lattices. One lattice is given by this gray dot, the other FCC is given by this black dot. And if there are two FCC lattices that are intertwined with respect to each other, first you basically merge them together, then you pull them apart along the body diagonal up to in a direction of 1/4, 1/4, 1/4. So the one FCC lattice is shifted 1/4 along the body diagonal with respect to the pristine FCC, and this is the structure of a typical diamond. Okay, it is a double FCC structure. Space lattice is still FCC, but there are two FCC lattices which are intertwining. Now it is very important and also certain times difficult, because see, all of these atoms are carbon. So how do you associate where which carbon is sitting? This becomes a tough job. Because if you have something else which is a diamond structure, for instance, if you look at, say, zinc blend, this also gives you a diamond like structure, but there are two atoms, zinc is there and sulfur is there, but in diamond it is all carbon. So you have to see how these are arranged. Now I'm trying to show you that a conventional unit cell contains about 8 atoms. Obviously it is not a primitive cell, there is no way to choose a primitive cell, and we don't even bother about that because we are happy with that. Now you look at, if you get rid of this double entwined structure, you will see that there are actually carbon sitting. See, some on the halfway path and some at 1/4 and some at 3/4. So see, there is one carbon which is here, which is 1/4 from the base. One carbon which is here, which is 3/4 from the base. One carbon which is here, which is at the face. One carbon which is at the bottom. So if I look from the top view, this is a top view. This is a top view. 0, 0, 0 red circle mean what is at the base, complete base. So this base, or 1. 1 and base are just coinciding on each other. So don't worry about that. But whatever is half means that the carbon is actually half moved with respect to the basal plane. So at the along this edge line, which are these green dots, look at these green dots, 1, 2, 3, 4. 1, 2, 3, 4. These are the green dots which have actually gone up half. There is one at the top, which is this blue dot here, but this is also 1 or 0. It doesn't really matter. So the basal plane is the red, half elevated carbons are there along the edge lines, along the faces, one at the top face, one at the bottom, but that coincides with each other. However, there are these, say, look at these small green ones here, this one here, this one here, this one here. They are actually either 1/4 above, because you have actually shifted that lattice 1/4, and some are 3/4, which means they are actually from the top, it is shifted 1/4 below. So these are this carbon is 1/4 above. On the other hand, this carbon is 3/4 above. So you have along these lines in between the lattice, uh, overall carbon position at 1/4, 1/4, and 3/4 and 3/4. This is just the top view, and this is how exactly the three-dimensional thing looks like, right? So if you look at it, you are looking at the different carbon at the edges, carbon at the faces, and also carbon sitting in between the FCC lattice. That is why you have total 8 atoms sitting in it. Okay, so 8 atomic contribution to this unit cell is there. Obviously, you cannot even think about a primitive lattice in this kind of situation. One very important thing about diamond is that although diamond is one of the hardest material known, you probably know that it is used to cut like glass and stuff like that. It's very, very difficult to crush it. But you will be surprised to know that it is one of the most loosely packed structure, and the packing fraction is really low, 0.34, 34%, compared to an FCC or an HCP structure which has 74%. It is only 34%. So the big question is, if something is so loosely packed, 34% means what? 66% is vacant. Now the question which is important to answer, and I will not give the answer right away, we will discuss it at the end of our lecture series, is that why then diamond is so hard if most of the material inside is just air or vacuum? Right? Think about it. It's a very important thing that comes into mind, that although it is one of the hardest material and one would expect that this might be the most densely packed material ever, however, it is not the case, because this only 34% packed, the rest of it is actually vacuum. So ideally, if it is not so closely packed together, it should be brittle or something, but it is very hard, because there is something else that plays a role into it. And I won't give the answer now, but at the end of the lecture we'll discuss it. So please think about it. I will seek your opinion on this at some point of time, what you think is an answer for that. Okay, just to show you a little bit more clearly, look at here, I've tried a little bit as much as possible to be visually more appealing. So the two atomic bases will be this 000 and 1414. So this is one and this is another, right? This is my basis, the two atomic basis for that, but they are both are carbon, they are same atoms. And you see here, there will be these blue atoms which are 1/4, 3/4. There will be these green atoms which are sitting at the faces here, 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 and here. So finally, you look that a conventional unit cell, this is what looks like, and the underlying structure is an FCC with a two atomic basis, right? Now see, here also there is one carbon which has like 4 bonds. Here there is one carbon which is 3/4 above the basal plane, This is also 4 bonds. Here again, this is at this edge. So you look, this one is at this corner. This one is connected to this corner. This one is connected to this corner, and this one is connected to this corner. So eventually, you see, if you put them all together, these are all carbons, although they are shown in green and blue and red. But this is just to show you what are the different configuration in which this bonding is happening between the carbon atoms. This is exactly the diamond, how it looks like in the structure, right? It is a tetrahedral structure which each atom surrounded by 4 equal distance neighbor, as you can see, 4, 1, 2, 3, 4. And this is the typical tetrahedral bond that is formed. I already gave you a hint, but maybe you can use this hint to think why diamond is so hard. And it has to do with the tetrahedral structure that you see because of the 4 nearest neighbor that the carbon is actually bonding with, right? Example 4, cubic zinc blend. But unlike carbon here, the advantage or the disadvantage, whatever you call, is that these carbons that we were seeing were the same. This was also carbon, this was, now this is, if this is zinc, this is sulfur. So you have to think about these 4 sulfur atoms, which are 4 molecules of zinc sulfide in each unit cube. So you have to find the position of zinc 000 with respect to sulfur 141414. Then you have to find zinc 0 half half, find another sulfur which is 143434. So you will have actually, just like sodium chloride, there are 4 units where zinc and sulfur are connected to each other, one here, one here, one here, one here. All of these zinc and sulfur are connected through these points in the space, and all 4 of them will be required if you need to know what are the coordinates of the bases into it, right? So this is what the zinc blend structure or zinc sulfide structure is known as. It is one FCC. Zinc sits on one FCC, sulfur sits on another FCC. They are 1/4 distance away along their body diagonals. And very important examples are silicon carbide, gallium phosphide, gallium arsenide. So see, these are the materials that you are using almost in a day-to-day life, right? People were talking about quantum structures, quantum wells, quantum technology. So for quantum wells and emitters and all of these, people are using a lot of these semiconducting materials also, right? So the importance of this is that how these structurally, how they are actually forming. For instance, gallium arsenide, gallium indium arsenide, they are used as quantum wells for lasing. So if you don't understand the crystal structure associated with that, how can you even explain the process of lasing and stuff like that, right? So all of this quantum phenomena is happening, but the structure lies basically in a lot of these cases at the heart of it. Okay, right. So I think we have now passed on to the point where we can discuss a little bit about the reciprocal lattice. This is, the one of the main important parts of this condensed matter solid state physics lecture. So typically, I think there were 1 or 2 people who are asking that how we can find this structure. We are talking about crystal structures where they are BCC, FCC. How do we know whether it is BCC or FCC? How do we know that it is something else, right? So the one silent experiment which has been doing it for years now, hundreds of years, is X-ray diffractions, right? What do? You put your crystal, which is say size A, and there are certain planes, 011 plane here. Now you take an electromagnetic radiation, in this case X-rays. Why? Because the wavelength of the X-ray is actually similar to the lattice spacing of the crystal you are probing. Okay, if you use too big or too small wavelength, then they will not be commensurate, and you will not be able to, for the interference to be happening, the wavelength should be commensurate with the unit cell dimension. So wavelength of X-rays, it varies, but typically you can think 1.5 angstrom about for copper K alpha. Most of the lattice constants are 3 angstrom, 5 angstrom, 2.5 angstrom, and so on and so forth. So this distance between these atoms, or interplanar spacing, is of the distance of angstroms, and hence X-rays are extremely well suited. Another very good source which can be used to look at these structural determinations are neutrons. Okay, so neutrons also have similar wavelength, and in addition to giving you structural information, the lattice parameters, and telling you whether it is FCC or BCC and what symmetry it has and what not, it, because there's a neutrons has this nuclear magnetic moment, so it interacts. If your material is magnetic, then it will have a magnetic interaction, and extra information about certain things you can also get from there. But the concept doesn't change whether it is an X-ray or a neutron. You talk about the wavelength, which is commensurate with your interlattice spacings. And when this interacts, and I'll show you how it is interacting, you go to a particular pattern, right? So if there's an X-ray in your sample and you are, say, collecting a 2D pattern, and then in the 2D pattern, you see that there are different spot things that you get here. These are known as the Lavais spots or observations, right? These were observed about hundreds of years ago by Lavais, in 19 Lavais, and then Bragg and stuff. And now from these spots and the position of the spot and the symmetry of the spot, you reconstruct your crystal structure. This crystal structure is, I am just imagining here, this is just a crystal. I don't even know whether it is cubic or hexagonal or what. I'm using X-rays impinging on the material. Then I'm getting this pattern. Now I have to find the mechanism, the algorithm through which I can reconstruct or analyze the symmetry, the distance, the intensity of these spots to reconstruct the crystal structure. This is what is unknown to me. And this is what I'm sampling with. I have an unknown material, impinge X-rays, I look at the pattern, I find a way in which I can reconstruct or analyze it or fit it or whatever you call it to find this unknown crystal structure. And that is the goal for X-ray crystallographers, X-ray diffraction. Whatever you do is mostly about trying to understand or investigate that what is the crystal lattice about. And if you have a known crystal lattice and you have exposed them to certain other experimental conditions, or the crystal has strain or thermal expansion or defect or whatever, it will tell you also accordingly, right? That whether it is a pure crystal, whether it is an impure crystal, whether there are defects, and so on and so forth. So many things can be studied using this X-ray diffraction techniques. It's an unbelievably technique. I mean, so common that almost every lab in every institute has them, and it is used routinely. One of the most used undestructive technique. If you can also get this information from, say, TEM, transmission electron microscopy, or atomic force microscopy. But first of all, atomic force microscopy is a top probe, so you only look at the top surface. So if there are crystal planes are not arranged in the top surface, you won't see it. You only see a morphology, right? Scanning electron microscope doesn't have the resolution to go up to lattices. But for transmission electron microscope, yes, you can see, visualize them very good. You can see atoms and the planes sitting together, but it is a very local probe, which means that, for instance, if there is a heterogeneous sample, some position is very good, some other position is not so good, then you can actually be easily confused by what exactly is your crystal structure. So as long as, if you want to probe nanoparticles or other things, transmission electron microscope is a wonderful technique. It's a kind of seeing and believing things. But by and large, because, and also for TM, your sample has to be more sacrificial. It has to be transparent to electrons. There are a lot of processes involved in how you prepare your samples for transmission electron microscopy. And in that case, in some cases, your sample also gets degraded because it is high energy electron bombardment that happens to your sample. X-rays, on the other hand, if you do not overexpose yourself, are rather, I would say, not so detrimental to your sample quality. Particularly if there are inorganic elements, then they are not known to make too much of an harm. But overexposure can be, again, harmful, right? So you can use X-rays, neutrons, electrons. Even in transmission electron microscopy, where you use electrons, you can not only look at the image in the plane, you can also look at the diffraction of the electrons, because wavelength lambda is of the order of your A, or the interplanar spacing, right? Great. So what I'm showing you here is the so-called thing, the Bragg's law, which is probably one of the most recognizable equations that you'll ever see. And it's unbelievable that which was proposed by William and Henry Bragg more than 100 years ago, right, it still holds true. Even today, the 2D sine theta equals to n lambda, this equation is still used by the most complicated of crystallographers to solve crystal structure. So imagine that it has gone through the tests of time, and the complexity of crystal structure these days is immense. Those days you had like gold, palladium, platinum. These are one atom, two atoms maybe. But nowadays you are doing protein crystallography. Do you know how many number of atoms are associated with one basis in a protein? There can be hundreds, there can be thousands. So imagine what a complex crystal structure you are forming. And imagine that you are doing X-ray diffraction from that, looking at the patterns, and being able to reconstruct the protein structure, which talks about protein denaturations or other things and gives you valuable information, right? These days, a lot of people who work on these proteins and other and how they function within the body use X-rays to a large extent. I mean, it has gone beyond material science and applied physics to all perspectives of sciences where you can explore them. And it is based on very simple logic that, if there are planes of atoms sitting together, X-rays are impinging at a particular angle, say theta incident or I, and there is a lattice between these two planes. There's a distance which we say d. HKL is the plane. So these two planes are defined by my HKL Miller indices, as I already explained, and this is the interplanar spacing, and these are getting towards the detector. What happens is that there is an extra path length that is covered because this ray travels longer into this crystal. You have an extra path length that incurs an extra phase difference, right? And constructive interference only happens when the path length is an integral multiple of the wavelength impinging, and hence if theta incident and theta initial and final is equal to theta under specular condition, your path length becomes 2d sine theta, and hence 2d sine theta, this extra, it's very easy to calculate. 2d sine theta equals to n times lambda. So this is the Bragg's law. This holds true, and it's extremely relevant. Only one thing I want to tell you here is that, and probably it might come a little bit as a surprise, this is slightly incomplete in its explanation of X-ray diffraction, because in X-rays you also use them mostly for identification, isn't it? You want to know whether it is gold or platinum or copper or things like that. But look at this equation. In this equation, is there any information of what this material is? It is not, right? It is saying that whether I put lead here or I put aluminium here, it doesn't matter. Of course, you can argue that for lead and aluminium, the DHKL value will change, the sine theta value will change, and all. I understand, but hypothetically speaking, it tells you about the. It only says that it is only dependent on D. It does not tell you that different materials can scatter X-ray differently, and we know that it is very true, right? Because when the X-ray is impinging on you, the materials, the electrons, actually they absorb it, and that is what it gives you the signature, right? The scattering amplitude should carry, the scattering amplitude here should carry the information of the material with which is interacting with. Otherwise, how can I even identify that whether I am scattering from gold or from aluminium, and with both of them having the huge difference in electron density, right? One is very heavy, the other is light, and things like that. Hence, the total diffraction idea is a combination of arrangement of atomic planes as well as the individual scattering power of the atoms formed on this atomic plane, which in this case is not considered in the Bragg's law. So essentially, you need to go a little bit one step further, to be able to totally understand the diffraction dynamics, right? So you have to go beyond Bragg's law and understand that composition matters, whether it is aluminium or whether it is lead or whether it is some alloy or whether it is more than one kind of material. They all absorb and interact with the X-rays in a very different way, right? So it is, you have to understand things. So, and later on I will explain to you that these are two main aspects about it. One aspect is when you have particularly the atomic arrangements, and the other aspect is when you have what this material is actually made up of, right? So these two are very important, and in this case the scattering wave amplitude which carries the signature from the basis of atoms is important, right? So let us try to see what is this scattering amplitude, what information that scattering X-ray is actually carrying with it, and how we can actually find a way to understand about the scattering power of this material particularly. So we have defined already the vectors T, which is U1 A1 plus U2 A2 plus U3 A3, right? Which means from here to here, if I want to go to from one atomic lattice site to another, I can easily go using something known as a lattice translation vector. Of course, these U1, U2, U3 are all integer values, right? Which means in this case, U1 will be say 2 times A1 plus 1 times A2, right? So from here to here, you can go to any position by going in these integral values, okay? And because it is, a crystal is translationally invariant, all local properties associated with the lattice should also be invariant. In other words, things like charge concentration, electron number density, all of this should also be invariant. And this is what we can exploit to understand the scattered wave amplitude more. So I'm just going to go through a little bit of the facts about what exactly information the scattering wave amplitude carries in a slightly more mathematical way. So, but it's not so difficult to follow the logic actually. So even if you're not understanding going through the full thing, you I hope you will understand the essence of how, when I detect the X-ray using my detector, what information about this particular sample my X-ray scattering amplitude is carrying about. Okay, so I will look into the periodicities where I'm looking at a number density n, which is a function of r, but my claim is because it is translationally invariant, nr plus t should also be equal to nr, right? So I'll start with a one-dimensional. So instead of going into 3D, I start with 1D, I establish my situation, and then I can actually translate it to 3D very easily. Now you all know about the Fourier series expansion. So you expand nx in this Fourier series, so n naught plus some Cp and Sp, which are basically certain constants, and based on that you can easily create a cosine and sine functions, and you add additionally a 2 pi by a factor, because gradually you want to put it by hand, because you understand that whenever you go from a one Fourier space to another, this 2 pi by a factor comes into this picture. It will later on be helpful. So my nx is defined like this, and I just say nx plus a. Nx plus a is, say, a periodicity for a one-dimensional lattice. What we do is that we add this a here. So x plus a, instead of x we now add x plus a, but you see that this is only twice pi times certain integer p, so which doesn't really change my angle much, isn't it? So the Cp cos a plus twice pi some integer is exactly the same angle. So it turns out that this is n0 Cp cos px by a plus sp sine 2 pi px by a, and which is exactly what is the value of nx. So essentially, we don't bother too much about it. We have been able to establish that nx plus a is actually equal to na, and that is the one point about it. So I will designate the twice pi pi as a point in a real space. So I have a space which is in real space is a separated a, but now I can do a Fourier series analysis and create a space which is 2 pi by a separated, okay, in one dimension here, and I can do this in 2 or 3 dimension very easily. But you also know that you can very easily generalize it. Instead of writing in the terms of sine and cosine, you can write it in terms of e to the power I, this angle. So generally you can write nx as np e to the power I 2 pi p x by a, and in 3D you will see that n of r is actually a three-dimensional quantity now, can be given by the summation over ng e to the power I g dot r. So this is a very generic way in which there is a Fourier analysis of this periodic function. The only thing that I need to know here is what is this g. Find the set of vectors g which is invariant under crystal translation, and this g will guide me how my reciprocal space will look like, whether or not there will be diffractions, or just like you could find a translation vector in real lattice, you can also create a translation lattice in reciprocal lattice, and this g is going to be my lattice translation vector. Okay. So both in terms of t and g, I've been able to understand. So you can easily imagine that this is the kind of information that my scattered amplitude will carry, and from this I can very easily establish. So this is just an inversion of the Fourier series, from which you can go from np. If p not equal to p prime, you can go to so you can go from nr to ng, and you can do an inverse Fourier series. You can go to ng from here. Only you have to divide it by the cell volume cell. So this is not important. What I'm trying to say is that it looks very similar to how you do your Fourier transformation, right? Fourier analysis. So we are going from real to reciprocal just by doing a Fourier transform of the electron density distribution. Look, this nr is what? The number density, or how many number of electrons available in the real space. So from there you can go to n, which is available number of electrons in the reciprocal space, just by doing a Fourier transform, right? That is the link. That is the interpretation that is happening. So I now have gotten one first hint about how to convert the data which looks like this dotted Lawes pattern to try to find out whether I can generate a real lattice vector, a real space, and a real unit cell corresponding to those points, because I know that they are connected by the Fourier transformation. So just see what I do. Just like in real space, I have T, which is U1, A2, A1, U2, A2, and U2, A3. And in G also, similarly, because obviously the length scales will be different and it is actually inverse length scale because it is twice by A. You will see from going in real space from one point to another, you can go using T. Similarly, you from going from one point in reciprocal space to another, you can do anything using G. However, if you try to go somewhere in between where G is not defined, that is not part of the reciprocal space. That is the important thing. Okay, there cannot be any point in between where if your lattice translation vector can't take you, that is not an acceptable translation vector in either real or a reciprocal space vector. So all we need to find is what are our A1s, A2s, A3s in real space, and what are our corresponding B1, B2, B3 in the reciprocal space. Remember, now my lattice has changed significantly to a reciprocal lattice. Now I have to work also think in terms of B1 and B2, which define the primitive reciprocal lattice and stuff like that, right? So my job, just like in my job in real space, was to find A1, A2, A3 with some corresponding U1, U2, A3 just as a translation vector. I have to find G, and for that I have to create B1, B2, B3 from known values of A1, A2, and A3, right? Can we do this? It turns out that we can, and we have all learned about this in our vector algebra chapters, I think class 10 or 11, wherever this is. So any lattice vectors or set of lattice vectors, if there are A1, A2, A3, you can create another set of lattice vectors B1, B2, B3 just by using these formula. A2, A2 cross A3 by A1 dot A2 cross A3. For B2, it is A3 cross A1, and for B3, it is A1 cross A2, right? So I now know that if I am sure about my real space axis vector, lattice vector, I can create a reciprocal lattice vector B1, B2, B3, in which the reciprocal lattice is defined by the G vector. Only one condition I have to satisfy, that Bi dot Aj should be equal to twice by Ig. This is a condition of orthogonality, that you are aware that it will only be 1 when I equal to j, it is 0 otherwise. Okay, so whenever like Bi into Ai, it will have value 1, Bi dot Aj will give you value of 0. So under this condition of orthogonality, you can create a set of reciprocal lattice vectors from a known set of real lattice vectors, such that you can define a reciprocal lattice vector G, which is nothing but a lattice in the Fourier space associated with the crystal. So I have a lattice in real space, that T defines that lattice. The moment I do a Fourier transform and I go to another space, which is my reciprocal space, I have to define a specific reciprocal lattice vector, which helps me go from one reciprocal lattice point to another. Okay, so this is basically about vectors in G. So you can easily see that when we are trying to again see whether my electron density is conserved in also in the reciprocal lattice. So nr is defined by ng to the power I g dot r. This I already defined. So what happens if I do a translation? R plus t, G r plus t, you can define e to the power I g dot r plus e to the power I g dot t. Now look, define how we have defined G and T. E to the power I G dot T is nothing but V1, B1, V2, B2, V3, B3 dot U1, A1, U2, A2, U3, A3. Now, if I look at the orthogonality condition, you will see that it turns out to be twice by V1, U1 plus V2, U2 plus V3, U3. So this is V1, V2, V3, U1, U2, U3 are integers. Product of integer is also an integer. Sum of products of an integer will also be an integer. So if you have e to the power I times twice pi times some integer, what should it give? It should always give you 1. So if this term reduces to 1, it means that nr plus t is equals to nr. So Fourier representation of a periodic function can contain components only if your reciprocal vector is well defined in terms of v1 b1, v2 b2, v3 b3, where b1 b2 b3 can be created from a1 a2 a3, and commensurately v1 v2 v3 should comply with this particular setup, only if e to the power I g dot t equals to 1, then only it is a proper Fourier representation, right? And this, you will see that this is actually a first hint towards giving you an idea about when should you expect some kind of a diffraction. So diffraction condition, of course, that this is the next thing that one thinks about, that what do you talk about in a diffraction condition, right? So there is a theorem which says that the set of reciprocal lattice vector G determines the possible X-ray reflections. Now, at first instant, it looks a little bit weird. We are coming from a concept about Bragg's reflections and refractions, where we see 2D sine theta, and suddenly we are in this G domain, isn't it? But we need to know to understand the algorithm of G, because remember, our data, the Laue spot that you get, is actually something that one is best visualized in the reciprocal lattice. So I need to know the language between going from real to reciprocal lattice, at the same time coming back from the reciprocal lattice, to be able to generate that crystal structure that I'm trying to find out, right? So particularly, say, imagine there is a small elemental volume dV, there is an incident wave front coming from plane wave e to the power I k dot r. It is diffracted from here and from here. It is making a certain angle phi. This is k. This is k prime. Although the directions of these two vectors are different, under elastic scattering we know that their actually modulus is same. This is elastic, so which means there is no energy loss. So the incident wave front is e to the power I k dot r. The exit wave front is e to the power I k prime dot r. So when is the good diffraction condition happening? Again, it is the same thing, that if you create two different paths, it creates different path. There's a path difference. Path difference creates a phase difference, and the difference is phase factor between 2 points scattered from 0 and dv, which are separated by some distance r, is e to the power I k minus k prime dot r, right? This is the phase factor that comes. You know about these things. So not only the phase depends on e to the power I k minus k prime dot r, but it also depends on the scattering vector. It also depends on the number of electrons associated around that point, which is nr, isn't it? So when you look at this nr, number of electrons scattering, as well as, so this gives you the phase, this gives you the amplitude. So finally, if you look at the total amplitude along k prime, it should be proportional to not only the electron density distribution along this dv, but also to the phase factor. And this is where we define a quantity known as a scattering amplitude, f, which is nothing but the integral. Now you found it for an elemental volume, you integrated over the whole thing. So you integrate over dv nr e to the power I k minus k prime dot r. So this is essential. The scattering amplitude is this. This is what you are actually, your detector is looking at. Of course, it cannot detect an amplitude. It is always detecting an intensity. But this is the information that it is being carried about. And in this information is also hidden the scattering condition, that whether or not this will give me a peak or not. Right? Now, k minus k prime, if you just look at the vector diagram, it is just delta k, which is the change in this direction, right? Some people also call it q. Let us, for the time being, call it delta k, known as the scattering vector. So you can just replace your k minus k prime by delta k here. There's with the minus sign, just to make sure that the directions of the vectors are properly preserved. You know your how nr is defined, ng e to the power I g dot r. So you replace the nr with ng here. So what do you get? You get the summation over g, you get the integration dv ng e to the power I g minus delta k dot r. So you see, you have now the reciprocal lattice vector g, the scattering vector delta k, and on the condition when delta k equal to g, this becomes 0 or 1. And if you integrate, your total scattering amplitude is now nothing but the total number of electrons or number density times that over the total volume. So this is per unit volume, this is total volume. So your scattering amplitude must be this, right? How many number of electrons scattered over the total volume. But when is this happening? When is this maximum? Only when delta k equal to g. If delta k varies significantly, if delta k and g are not matching, then this will basically die out, it will oscillate out, which means it will give you almost no or zero peak or noise level peak. So f can be very small, scattering amplitude could be very small or considerable and substantial, depending upon whether delta k is equal to G or not. And this is exactly, you can see that both of them are actually not very different. There is an equivalence between something that is known as the Bravais diffraction condition that you can see here, and the Bragg's diffraction condition that we have already discussed. And we will discuss this also a little bit, time permitting, right? So what you do, if delta k equal to G, you just put the value of delta k minus k prime, so k plus G equal to k prime, and you just do a square of these two, right? You know that since the modulus is same, the modulus of k square is also the modulus of k prime square is same. So you k plus G square equal to k square, or 2k dot G plus G square is 0. Since G is a reciprocal vector, minus G is also a reciprocal vector, because T and minus T is also a translation vector. So you come to the diffraction condition of 2k dot G equal to G square. Now this is the diffraction condition that we have established independently from the perspective of a reciprocal lattice, and it is exactly equivalent to what you get for Bragg's diffraction condition 2d sin theta equal to n lambda from the real lattice, right? So you look at the one-on-one course. This is the Bravais diffraction condition, that was the Bragg's diffraction conditions, and although they have been developed by completely different ways or formalisms, this being a more generic way of discussing and taking into account the scattering amplitude, which also has in its the change in the phase and the electron density distribution information ng, this is more generic, right, than that Bragg's diffraction condition. You will see that both of them are actually equivalent in their nature, right? So I just want to have this a quick proof that the spacing DHKL between planes is normal to the direction this. So the DHKL is defined by twice pi by G, right? You see this is our direction of incoming X-ray scattering, exit X-ray scattering. The distance between them is delta k, or we know now that delta k equal to G. So if DHKL is twice pi by G and 2k dot G equal to G square, you expand this, 2k times G sine theta equal to G times G, 2k sine theta equal to G. You know what k is. K is a wave vector, so it is twice pi by lambda. So 2 times twice pi by lambda sine theta is twice pi by DHKL, and voila, that is what you get. 2 DHKL sine theta equal to n lambda. You are getting it exactly from this diffraction conditions or Bravais diffraction condition that has been completely independently derived using totally different perspectives of scattering. Remember, how were you scattering using it? See, you were using a most generic way. You did not say any plane, you did not assume anything else. You just say that this is from 2 points, the scattering waves are coming and interfering with each other. When will they interfere constructively or destructively? That is your condition that you have been able to derive using this equation. And it so turns out that this is nothing but very, very Bragg's condition that we already discussed, right? So I think I will stop here. And if there are any questions or something, I'm happy to take, because I've been advised to leave 5 minutes for taking in some questions and all.
Yes. Indeed, a great session. Professor Banerjee, can you hear me? Ankita, can you hear me?
I think I can stop sharing perhaps, or let's see if there are any questions.
Yes. Why I'm not audible?
Sir, you.
Ankita, can you hear me?
Yes, sir, but your voice is very low.
My voice is very low. Okay. Problem. I have to change the camera. Now it is good. Now can you hear?
Yes.
Yes, sir.
Okay, good. So thank you, Professor Banerjee. Indeed, it was a very informative session, and the way you covered all the topics, it was wonderful. And now this session is open for questions. So I'll take the question one by one for this session as well as for the previous session. and I would like to try to take only the relevant question relevant to the topic of these two lectures. So I'm just scrolling down the chat window to see the questions. Uh, People are asking a lot of question about the Canvas LMS. Canvas LMS is having some problem from Canvas administration side. We mostly people are asking questions about what.
Sir, your voice is not clear.
Okay. Ankita, is it clear? Can you hear me now?
Yes, sir. Now it's clear.
It is better before. Ankita, can you hear me?
Yes, sir.
The voice is clear?
Now it is clear, sir.
Okay, maybe it's seems some internet connectivity issue because the video is also not going continuously. So, Professor Banerjee, for first question is that one candidate is asking with these parameters, like in your previous lecture, you told to calculate these all lattice vectors, direction, and Miller indices. They are asking how can we estimate the physical and chemical properties of a material?
So, from direct lattice spacing, you cannot estimate any physical or chemical things. This is just the way the material is organized. Okay, if it is organized in say some cubic form or orthorhombic form or tetragonal form, it is just the way that the material is actually forming in three-dimensional space. Okay, now due to their specific ways of organization, they may show some specific properties or not, but just by looking at a plane you cannot say. If you think in terms of growth, why a particular, say you are growing some kind of a nanomaterial, it might grow along one particular direction, it might show a specific orientation. In those cases, those planar directions become very important if you are analyzing TEM data, because you are actually projecting it along a particular plane, right? So crystal directions and planes are very important for crystal growth, to understand the growth. This is more important for people who are doing more of a synthesis or growth strategy. For more information, whether it is will be magnetic or not, whether it will have superconducting properties or not, whether it will be a good thermoelectric properties, you have to go beyond the crystal structure. And of course the crystal structure will also tell you whether it is like, semiconductor or insulator or what. So it tells you about the different material properties, but you have to go beyond that, about the energy level alignments, Fermi level